So here we'll check out problem 6. This is from the 2011 BC exam. This appeared on Form B. It's a non-calculator question, deals with Taylor series. And so all they really do for us to start is they define the function f of x here. And then in part A, they tell us the Maclaurin series for the natural log of 1 plus x is given by this. We want to use this series to write the first 4 non-zero terms in the general term of the Maclaurin series for f. So what I did is I went ahead and I called h of x the natural log of 1 plus x. And then the relationship between f and h would be I simply have to put x cubed in place of this x right here in order to go back and forth between f and h. So f of x is equal to h of x cubed. It's this series with x cubed in place of all the x's. So if you put x cubed in place of all the x's in the series for the natural log of 1 plus x, you end up with this initially, and then if you clean that up a little bit, it looks like what I have right here. So part A shouldn't be too bad. You're just replacing all of the x's in this series that converges to the natural log of 1 plus x with x cubes. In part B, they wanted us to figure out what the interval of convergence for this series actually is. Now they were nice and told us that the radius of convergence is 1. Well, since this series is based at 0 because it's a Maclaurin series and our radius of convergence is 1, we know the interval of convergence has to go from -1 up to 1, right? Up 1 from 0, down 1 from 0. Now this is the final answer right here, and I did not know if I could include -1 or include 1 right away. We have to manually consider what's going on with those endpoints, because at those endpoints the ratio test would be inconclusive. Your limit from the ratio test would equal 1. So when you manually put the endpoints of 1 and -1 in place of the x in the series from part A, when you put 1 in, you end up with 1 to the 3n, which is just 1, so that ends up being the alternating harmonic series that converges. So the series does converge when x equals 1. That's why I included that on the interval of convergence. But then when I considered -1, if I put -1 in place of the x, if you multiply these pieces together right here, that's multiplication of like bases. You can add those exponents. So you get n plus 1 plus 3n, which gives you 4n plus 1. Now what I noticed about this was 4 times any number is always going to be even. And then if I add 1 to an even value, my result is always going to be odd. -1 to a power that's always odd is going to be -1. This is really -1 times the harmonic series, and since the harmonic series diverges, so does this. And that's why I did not include -1 on my interval of convergence up here. So the tricky thing here is recognizing that you have to consider the endpoints and whether or not they can be included within the interval of convergence. In part C of this, they asked us to write the first 4 non-zero terms of the Maclaurin series for f prime of t squared. So what I did first is I took my answer from part A, the Maclaurin series for f, brought it onto this screen, and then I took f prime of x. So when I took the derivative, what ended up happening was by just using the power rule a bunch of times, I generated this. And then if you just simplify that, 6 over 2 gives you a 3, 9 over 3 gives you a 3, 12 over 4 gives you a 3. If you cancel this n with that n, you're just left with a 3x to the n minus 1. This would be the series for f prime of x. We wanted a series for f prime of t squared. So then I just had to, like we did in part A, I would have to take the series for f prime of x, and I'd have to replace all the x's with t squareds. So I replaced all the x's in this series with t squareds, simplified, and that left me with this. And then it wants the first 2 terms of that series to help us approximate g of 1, given that g of x is defined in this fashion. So I took my series for f prime of t squared, tossed it in place of f prime of t squared. I did my antiderivative using the power rule the same way I normally would, right? Add 1 to the exponent, divide by the new exponent, add 1 to that exponent, divide by the new exponent. This is the piece that got a little bit weird. Added 1 to this exponent, gave me 6n minus 1, divided by that new exponent. I had to evaluate this at x and at 0. Well, if I'm trying to estimate the value of this integral with the first 2 terms, that's going to be these 2 pieces evaluated at x evaluated at 0 makes these two terms disappear. And then if I want to estimate g of 1, I would put 1 in place of these x's. And when I put 1 in place of those x's, I get 3/5 minus 3/11. Find your common denominator, do your arithmetic, and you get 18/55. Now in part D, they want us to take the fact that the series in part C is a converging alternating series. If it's a converging alternating series, what can always be used to establish your error bound is the value of the first term that was left off. I didn't actually have the first term we left off in this estimate written out here, but if you think about the next piece that would have been within this series right here, it would have been a plus 3t to the 16th. And then if I do the antiderivative of that, I'd get 3t to the 17th over 17. And if I put 1 in place of that variable, I end up with 3 times 1 to the 17th over 17. 3 over 17 is kind of close to 1/5, but it actually is a little bit beneath 1/5. This has a value of about 0.17. So we do have an error bound established that is less than what they required of us here. And again, that's the converging alternating series error bound, not the Lagrange error bound. If we would have gotten, say, 4/17 and we wouldn't have had the inequality the right way, 4/17 would be slightly bigger than 1/5. We might have had to go through the pain of trying to establish that Lagrange error bound. But if you have a converging alternating series, and they kind of gave it away here that that's what you were supposed to do, always try to establish your error bound the simpler way, and that's with the value of the first term that's been left off.